The anatomy of brainstem reflexes. Ooh, brainstem, neuroscience, neuroanatomy. But the brainstem is where a lot of interesting things happen. Today we're going to look at baroreceptor reflexes. So how sensors in the neck and the chest carry information to the brainstem, how reflexes in the brainstem then feed back to the heart and peripheral blood vessels to manage blood pressure, with the example of what happens when you're sat in a chair and then you stand up, and how your body reacts super quickly to keep blood going to your brain, so you hopefully don't faint. Right, the anatomy of. Receptors in the body are part of the nervous system. So they are modified neurons, and they take information, they detect something, and they send that information back to the central nervous system. In the case of baroreceptors, which is detecting pressure, a baroreceptor, its sensory end is coiled, and it's in the wall of the structure. And in the case of the baroreceptors that are measuring blood pressure, they're in the walls of arteries. And those coiled sensory ends are covered in sodium channels. And that coil being in the wall of a tissue, as the wall of the tissue gets stretched, those coils straighten out. And as the coils straighten out, they fire off action potentials. So they send off that action potential, that signal, back up the neuron to the central nervous system. And the more stretched a stretch receptor is, the more often it fires off an action potential. So then the brainstem receives information about how stretched a material is by the frequency of action potentials that it receives. Do you see? So there is, in terms of blood pressure, these arteries have a certain amount of stretch pretty much all the time. And if they get stretched more a little bit, then more action potentials. If they get stretched a lot, lots of action potentials get sent to the brainstem. That's the sensory part of the reflex. That's the afferent bit. This means that the baroreceptors, the stretch receptors, and then the centers of the brainstem responsible for managing blood pressure are receiving information about mean arterial blood pressure and pulse pressure. Right, so where are these baroreceptors? Here's the thorax, here's the lung, here's the heart. I've taken the lung out on the left side, and in here we can see the aorta. So the heart is pumping blood out through the aorta, and the ascending aorta and the arch of the aorta are elastic. So it's able to stretch a little bit to dampen the pulsatile forces of the blood being ejected from the heart, which means that this is a little bit stretchy. In the arch of the aorta, we find baroreceptors. We find these stretch receptors responsible for detecting the pressure of blood as it leaves the heart. And this nerve here, running around the arch of the aorta, is the vagus nerve. Those baroreceptors send fibers with the vagus nerve up the neck. They run with the common carotid artery, the internal jugular vein, and then the internal carotid artery up to the skull. In here, we also find the chemoreceptors that we talked about in another video that detect the composition of CO2, O2 in the blood. Baroreceptors in the aortic arch. Now here is that common carotid artery running up the neck here with the internal jugular vein, and the common carotid artery is going to bifurcate at this level. Now look where we are, here's the mandible here, so we're quite high up. The common carotid artery ends by dividing into the external carotid artery and the internal carotid artery. The internal carotid artery is going to run up to the brain. Here, at this bifurcation of the common carotid artery, we have the carotid sinus. There is a slight swelling of the carotid bifurcation and the first part running up the internal carotid artery. And in that slight swelling, that's where we have more baroreceptors. So there are baroreceptors here in the carotid sinus, which are detecting the stretch of the wall of the common carotid and internal carotid arteries here, and sending that baroreceptor, sending that stretch information back to the brainstem. Now, the vagus nerve carried information from the aortic arch. That's cranial nerve 10. And remember, that's running up with these blood vessels into the skull. The nerve of the carotid, the nerve of the carotid sinus is called the nerve of the carotid sinus. And it's going to run and become part of the glossopharyngeal nerve, cranial nerve 9, which is also going to run up to the brainstem. The nerve of the carotid sinus is also called Herring's nerve, or the nerve of Herring. Fun fact, when we were talking about chemoreceptor reflexes, we talked about the Herring-Breuer reflex. That is just that, again, there are stretch receptors that tell the brainstem how stretched the lung is. So on inhalation, it's stretched, and on exhalation, it's not stretched, and that reflex triggers you to inhale when you've exhaled and to exhale when you've inhaled. The interesting fact is, Herring of Herring-Breuer was Herring of the nerve of Herring's dad. Wow, that's a really long way of putting that. Herring. It's not the same herring, it's nearly the same herring though. So the nerve of the carotid sinus, also known as the nerve of Herring, sends the stretch receptor information from the baroreceptors up with the glossopharyngeal nerve to the brainstem. Needlessly complicating things, sorry. So we have cranial nerves 9 and 10, the glossopharyngeal nerve and the vagus nerve carrying baroreceptor information up the neck, and they are going to pass through the jugular foramen. The jugular foramen carries cranial nerves 9, 10 and 11. This is where the internal jugular vein comes from. So those two nerves will go in through there, and then they are inside the cranial cavity and they enter the brainstem. Here is the brain, and here is the brainstem, and here are our cranial nerves entering it. Now remember that cranial nerves, like pretty much all the nerves in the body, are carrying lots of different neurons, lots of different fibers doing different jobs. So today we're particularly interested in the fibers that are carrying that baroreceptor information into the brainstem. And those baroreceptor fibers will pass into the medulla oblongata, and they will pass to the solitary tract, or the solitary nucleus, or the nucleus solitarius. Sorry, there are lots of words. Let's call it the solitary nucleus today. Now, the solitary nucleus is a collection of nuclei running up and down the pons and the medulla, and they are receiving sensory inputs. And sensory inputs into the solitary nucleus will then output to various other centers in the brainstem that are involved in regulating things in the body like breathing and heart rate. And that's what we're interested in today, is the heart and blood pressure, right? So our sensory baroreceptor information passes into the solitary nucleus and then links with axons, neurons that pass out to a region of the medulla called the caudal ventrolateral medulla, CVLM. Now, it sounds like a really long word, but it's just describing which bit of the medulla this is. So the caudal means it's to the tail. Rostral would mean it would be towards the beak. So basically inferior. Caudal ventrolateral medulla. Ventral, right, this is the ventral surface. This is the dorsal surface back here. So the ventral is anterior in the brainstem. Dorsal is posterior. Caudal ventrolateral. Well, lateral means it's to the side, right? It's lateral rather than medial. So this is a part of the medulla that is ventrolateral, and it's called the caudal ventrolateral medulla because there is a rostroventrolateral medulla. So our baroreceptor information, here's the medulla here, passes into the caudal ventrolateral medulla, and that then relays to a region of the medulla called the rostral ventrolateral medulla. Now this is the interesting bit because this is tied into the sympathetic fibers in the spinal cord. This will regulate sympathetic activity. So the sympathetic nervous system is famously distributed throughout the body to the smooth muscle of blood vessels, and the sympathetic nervous system can tell the smooth muscle in the walls of blood vessels to contract, so reducing blood flow through them. Right? So, how does this work? If the baroreceptors in the arch of the aorta and the carotid sinus detect lots of stretch, blood pressure is high, that information passes up the glossopharyngeal nerve and the vagus nerve into the solitary nucleus, which relays to the caudal ventrolateral medulla, which then inhibits the rostroventrolateral medulla, turning down sympathetic activity, which means the blood vessels throughout the body, arteries throughout the blood, but throughout the body, the smooth muscle can relax. The more blood can pass more easily through those arteries, so the blood is spread to the peripheries and blood pressure goes down. Does that make sense? Sensory input says blood pressure high, triggers turn off sympathetic activity to relax blood vessels so the blood can be spread throughout the body, so blood pressure goes down. Pretty cool, huh? That's not the end of it. In addition to that, those baroreceptor input fibers into the solitary nucleus also tie into the nucleus ambiguous. If you're associating the nucleus ambiguous with the vagus nerve, you're doing very well. So the fibers from the nucleus ambiguous then tie in to the dorsal nucleus of the vagus nerve. Now, the vagus nerve is the major parasympathetic nerve of the body. So what will happen here is that the parasympathetic fibers, so these parasympathetic motor fibers of the vagus nerve, will run with the vagus nerve down to the heart. So the heart has a cardiac plexus, the heart has the pacemaker, the sinoatrial node, and the effect of parasympathetic innervation on the heart is to reduce the rate of contraction, so to reduce the heart rate and to reduce the force of contraction, so reducing the cardiac output, reducing the output of the heart. So stretch receptors, baroreceptors say, ooh, blood pressure is high, feed that sensory information into the solitary nucleus. That ties into the nucleus ambiguous, which then fires off the vagus nerve to increase parasympathetic activities of the heart, which reduces cardiac output and reduces blood pressure. So if the sensors say that the blood pressure is high, the parasympathetic innervation to the heart will be increased to reduce cardiac output. Sympathetic innervation to the peripheral blood vessels around the body will be decreased to increase flow out throughout the body to reduce the blood pressure. Very cool. This baroreceptor reflex is a very rapid adapting reflex, rapidly adapting the cardiovascular system to changes in blood pressure. But when does this occur? How is this useful to you? What do you need to know? Well, can you appreciate, you're probably doing the same thing right now, you're probably sat down, watching a bunch of anatomy videos, and my heart is at this level, it's this high above the floor. The heart, of course, is a pump. It's pushing blood around the cardiovascular system, but a pump has to pull blood into it and push blood out of it. And a pump always has to work quite hard against gravity. So can you appreciate how high my heart is above the ground and what the column of blood is that the heart has to work on relative to gravity? And then if I stand up, my heart will be a lot higher. The column of blood with respect to gravity is much longer. My heart has to pull my blood up from my toes back into itself. And at the same time, you can think of this also as there's a limited amount of blood in the body. There's a limited amount of blood to go around, right? And it's just sent where it's needed. When I stand up, a lot of the blood in my thorax will fall into my legs because of the effects of gravity. Both of those things mean that the flow of blood returning to the heart will be reduced. There are stretch receptors in the atrium as well. This is called the Bainbridge reflex. This is another reflex for another day. Less blood enters the heart. This is what we refer to as preload. The heart is stretched less. This results in reduced output from the heart, right? If the output from the heart is reduced, then blood pressure will be reduced. But at the top of this column of blood is my brain, and I need to push blood at a pressure higher than the pressure inside the cranial cavity to my brain for my brain to continue receiving blood. So those sensors, the baroreceptors in the carotid sinus and the arch of the aorta, they're doing the opposite of what we were describing just now. They are detecting a reduction in stretch, a reduction in blood pressure. And that information then passes to the medulla oblongata. This goes into the solitary nucleus, but the input is different this time. The input into the solitary nucleus is fewer action potentials, a reduction in stretch, a reduction in blood pressure. This then passes to the caudal ventrolateral medulla, which then, instead of inhibiting the rostral ventrolateral medulla, stops inhibiting it, so that sympathetic outflow increases, sympathetic innervation to the peripheral blood vessels increases, causing the smooth muscles in the arteries to constrict, reducing blood flow to the peripheries, and forcing the blood, increasing the blood pressure centrally, so the blood pressure increases. Likewise, that sensory input that is now describing reduced stretch, reduced blood pressure, passes to the solitary nucleus, which passes out to the nucleus ambiguous, which passes out to the parasympathetic innervation through the vagus nerve to the heart, such that parasympathetic innervation is reduced to the heart, sympathetic innervation to the heart is increased, so the heart beats more rapidly and more forcefully to increase cardiac output to increase blood pressure. So very quickly the blood pressure is regulated when you go from a sitting to a standing position. Likewise, from lying down to a standing position. Can you imagine how lying horizontally to going standing up is more of an extreme change? This is the normal process. The blood pressure is managed so that it remains constant, it remains level, blood continues to pass to the brain, you don't notice that anything has happened. Occasionally, when you're tired or something might cause you so that when you stand up, you feel a little bit dizzy for a moment. That is like the slow version of this reflex. Your blood pressure is increasing, but there's a bit of a delay on it, so you feel a bit dizzy. And this is what we see in patients, particularly older people with postural hypotension or orthostatic hypotension. They stand up or they go from a lying position to standing up, and for various reasons the blood pressure is not maintained through the mechanisms that I just described. So blood flow to the brain is reduced, which might give dizziness, stars in your eyes, blurred vision, weakness, or it might even cause syncope in that you lose consciousness and fall over, you faint. Another reason why this information is useful clinically, and fun fact, right, we said there are baroreceptors in the aortic arch and at the carotid bifurcation. Now the carotid bifurcation is in a somewhat exposed location in the neck. What would happen with a blow to the neck at the site of the carotid sinus then? Well, so this person's got normal blood pressure, they're stood up, they're doing their thing, right? A blow to the carotid sinus would stretch rapidly the walls of the carotid sinus, the baroreceptors would be stretched, they would fire, they would send that information back to the brainstem. Those reflexes we talked about in the brainstem would trigger, okay, it thinks blood pressure is high, so it's gonna switch off sympathetic stimulation to peripheral vasculature, so blood will flow out freely through peripheral blood vessels, and it will switch on parasympathetic innervation to the heart to reduce cardiac outflow, to reduce the heart rate, and reduce the force of contraction, because the brainstem's reflexes are trying to normalize blood pressure. But in fact, the blood pressure was already normal. So what it's done is it's reduced cardiac output and sent blood out throughout the body to reduce the blood pressure. So that blow to those stretch receptors has triggered a fall in blood pressure to the point where blood is not at enough pressure to pass to the brain, and this will cause syncope. This will cause loss of consciousness and fainting. The other reason this is useful is because if you are with a patient that has low blood pressure, then be very wary of palpating this region here, because if you stretch the carotid sinus, then you could cause a further drop in blood pressure, which might not be a good idea. Okay, so there we go. That's the baroreceptor reflex. It's linking, so the afferent parts are the stretch receptors, the baroreceptors in the aortic arch and the carotid sinus, which send information through the vagus nerve and the glossopharyngeal nerve back to the brainstem, and then through those reflexes in those parts of the medulla oblongata that we talked about. The key idea is that they either switch on or off sympathetic outflow or parasympathetic outflow to the heart and the smooth muscle of peripheral blood vessels. Right, I hope that was useful. Let's get another reflex ticked off. I'll find another one for next week, no doubt.